So, a very good day to my examiners, the Associate Professor, TS Dr. Kan, and my supervisor, TS Dr. Lau Sei Ping. So, my name is Brendan Shankalat, and my metric number 83403, a final year student in the Network Computing Program in UNIMAS. So, today I will be presenting my final year project titled A Smartphone Assisted BLE Bluetooth Low Energy Beacon System for Locating and Managing Medical Equipment in Hospital. So this project is focused on leveraging the low-cost wireless technology to solve critical assets tracking challenge in the healthcare environment.
So we are currently witnessing a major digital revolutions in healthcare known as the Internet of Health Things (IoHT). So hospitals are transitioning from traditional facilities into some smart environments where digital systems are linked to physical assets to optimize operations. In this context, the ability to autonomously manage the hospital extensive inventory of mobile assets, specifically when the ventilators and also the patient monitors, infusion pumps, has become critical. So these are not just static items; they are moved constantly between wards. It's especially like the high stress area, like the accidents and emergency departments (A&E). So, however, my research highlights that the managing this asset is not just about the inventory control. It's a matter of patient safety. So the inability to quickly locate a ventilator during an emergency can lead to a serious treatment delays, which directly impacts the patient outcomes. So therefore, an automated tracking system is essential to prevent any this delay. So this lack of visibility of medical equipment creates three major problems that affect the entire hospital ecosystem. So first is in the clinical impact, whereas the most critical in high dependency areas like the A&E, accident and emergency. If a nurse cannot find a ventilator or infusion pass immediately, this causes treatment delays. So my research indicates that this logistical failure can directly compromise patient safety and outcomes. So especially for those in the critical conditions. So second is about the operational inefficiency. So this managed search processes place a massive burden on the staff, according to the key and time motion study by the Henbridge 2008. So nurse spends approximately 35.3% on their time on documentations and logistics, compared to only 19.3% on actual patient care. So every minute they spend hunting for device is just a minute taken away from the patients. So finally, there's a financial waste. This is often a hidden cost. When the hospital cannot find the equipment, they assume that the shortage exists and purchase or rent duplicates. So this leads to unnecessary capital expenditure on assets that the hospitals actually already owns but simply cannot see. So this leads us to the core technical challenge, which I call the infrastructure barrier. So currently hospitals are stuck between two extremes. On one side, we are manual tracking of barcodes. So these are chips, but fundamentally flawed because they are reactive. They only tell you that where an item was last scanned and not where it is right now. So if a nurse forget to scan an item during an emergency, the data is lost forever. So on the other extremes, we have a commercial real-time location system like ultra-wide and UWB active RFID radio frequency identifications. Both of the words can be found at the right corner with their full name. So these technologies are fantastic. They can pinpoint an item within 30 centimeters. So however, they come with a massive flaws, infrastructure dependencies. To make them work, you must have installed physical readers on every single walls or ceiling grids. So for a public hospital, there isn't just about the cost of the device, it's about the capital expenditure, capex of the drilling holes, running cables, or closing walls for renovations. This infrastructure requirements is the primary reason why the widespread adoptions have failed in cost-sensitive healthcare facilities. So my project aims to solve this specific barrier. To solve this infrastructure barrier I just described, I'm proposing a smartphone assisting BLE system, which is Bluetooth Low Energy Systems. So the core concept here is mobile crowdsourcing. Instead of spending 1,000 ringgit installing fixed reader on every wall, we simply use the smartphones that medical staff are already carrying. So we turn every nurse and doctor into a moving scanner. So here is how it works. So we attach a low cost ESP32 microcontroller to the medical equipment. So these act as our beacons. So unlike the commercial tags which cost hundreds, this costs only 20 plus ringgit and are fully programmable. So as the staff go about their daily rounds, their phones run a background service that passively listens for these beacon signals. So when the phones detect a ventilator nearby, it captures the signals and upload it via the hospital existing Wi-Fi network. Crucially, the system is passive, so the nurse doesn't need to open an app, press a button, or stop what they are doing. The system works autonomously in the pockets, so requires zero connective loads from the user. This effectively removes the high capital expenditure barrier and making the access tracking accessible for public hospital. So, in order to achieve the proposed solutions, the project is guided by three technical objectives. First is the hardware development. The goal is to design and develop a low-cost beacon using the ESP32 microcontroller. So this involves programming is to mimic the standard iBeacons of protocols, ensuring it can broadcast a stable, unique identifier for every piece of medical equipment. So second is about the mobile applications. So the objective is to develop a smartphone application specifically for the Android platform. So this app acts as a scanner. It must be capable of running efficiently in the background to detect these nearby beacons, capture their signal strength (RSSI), which is received signal strength indicators, and collect the necessary collection data without draining the user battery. And third is the system like integrations. The final objective is to tie everything together by developing a robust back-end server and device dashboard. So the server is responsible for the heavy lifting, is processing the raw signals and calculating the locations, while the dashboard provides a visual interface that allows hospital staff to see the real-time locations of assets on a map. So in my literature review, I perform a comparative analysis of the leading indoor positioning technologies to justify my choice of Bluetooth Low Energy BLE. So let's look at the technology comparison metrics. First, we look at RFID, radio frequency identifications. While passive tag are chips, the readers are actually incredibly expensive. Furthermore, it's not a true real-time system. It's a checkpoint base. So meaning that you only know where an item is when it physically passed through a doorway reader. If it moves into the room, you lose visibility. So next, I also analyze Wi-Fi fingerprinting. This is attractive because it uses existing routers. However, the literature confirms there's a downside, which is battery drain. Continuous Wi-Fi scanning is energy intensive and depletes the smartphone battery very quickly, so making it impractical for staff to use throughout the 12-hour shift. And then there's a ultra wideband UWB. This is a gold standard of positions capable to tracking items up to within 30 centimeters. However, it requires dense grip of expensive anchors on the ceiling. So public hospital, this level of positions is often overkill and financially unsustainable. So this brings us the Bluetooth Low Energy BLE, which I identify as a sweet spot. It strikes a perfect balance, and is significantly cheaper than the UWB and consumes far less power than the Wi-Fi. Where it may not offer centimeter level positions, but it reliably deliver room level accuracy, telling that you are exactly which what an item is in, and which is exactly what the hospital staff need to solve their search problem. So this slide is justify the two most critical technical decisions in my projects, the hardware and the architectures. So first, why did I choose the ESP32 microcontroller? Because the primary reason is cost. In my market analysis, I found that the proprietary medical grade beacons often cost upward up to 200 ringgits per unit. So for hospital needing to tax 1,000 device, there's a massive investment. So for the MSP32, however, costs approximately 20 plus ringgits. So beyond cost is about control. So commercial tech often come with a locked firmware where you cannot change the transmission power or broadcast interval. While the ESP32 is fully programmable, so allowing me to fine-tune the signal frequency to 100 milliseconds for smoother trackings, which is essential for my specific algorithms. So second, why mobile scanning? This is architecture was chosen specifically to solve the gateway dependency problems. So for the traditional system required to buy and install a fixed reader in every single rooms, by using the staff smartphone as a scanner, we achieve the infrastructure independence. We don't need to install anything on the walls. Furthermore, this model is inherently scalable. As you hire more nurses, you're not automatically add more scanner to your network, so improving coverage without spending a single cent on a new hardware. So to summarize the literature review, I have identified two critical gaps that this project aims to fill. First is the infrastructure barrier. As I mentioned earlier, almost every commercial solution currently on the market, whether it is active RID, is relies on the fixed infrastructure. So they require the hospital to install a proprietary gateway in every single room to detect assets. So for many public healthcare facilities, the cost of cabling, renovations, and system downtime is simply too high. So there's a clear lack of infrastructure-free solutions that can be deployed instantly using the existing resource. Second is the lack of end-to-end prototypes. Well, there's a plenty of academic research on ESP32 and BLE, Bluetooth Low Energy, but most is fragmented. So you'll find the papers that simulates an algorithm in MATLAB or papers that test just the hardware battery life. There's a significant scarcity of documented complete system that integrate custom hardware, a mobile scanning app, and a functional web dashboard into a single cohesive units. So my project bridged this gap by delivering not just a theory, but a fully functional and end-to-end working prototype. So for the development methodology, I adopted the phased prototyping approach. So given the complexity of this project, which involved custom hardware, mobile applications, and web server, a traditional linear model would have been too risky. So I broke the development down into four distinct phases. Phase one was system design and analysis. Here I focused on analyzing the requirements and designing the system architecture. I defined exactly how the data would flow from the beacons to the database before writing a single line of code. Phase two was the component developments. This is where the core engineering happens. I developed the three key components in a parallel. I programmed the ESP32 beacons to broadcast stable signals, build the Android scanner app, and set up the PHP backends. So developing them independently allowed me to isolate bugs early. So phase three was system integration. Once the individual components were stable, I connect them. Then I verified that mobile app could correctly read the ESP32 signal, that the server could receive the JSON payload from the app. And then finally, phase four was evaluations. This just involved field testing the complete end-to-end system in a control environment to make sure its zone accuracy and response latency, ensuring it meet the project objective. So to ensure the system solves these right problems, I performed the stakeholder analysis to understand who I'm using this for. Identify three key groups. First, our primary user, which is the nurse and ward staff. The pain point is that the daily frustrations of wasting time searching for items. The requirement is very simple. They need a passive system. They don't want to fiddle with the settings. They just need to see a green check marks and not it works. Seconds are the technical users, the IT the engineers. So their pain point is management. They are responsible for thousands of devices. They require an admin dashboard to register new beacons and crucially to calibrate signal sensitivity. Third is the strategic user, the hospital administration. They are less concerned with the app and more concerned with the bottom line. So their goal is to reduce the hidden cost of repurchasing equipment that isn't just actually lost and misplaced. So before moving to the architectures, we must define the system constraints. So first is budgets. The solutions must remain affordable for public hospital, which is why we strictly use the ESP32 microcontroller with 20 plus ringgits instead of expensive proprietary tax. So second is physics. Hospitals are full of metal beds, so the system must handle the multiple fading, where signals bounce and fluctuates. Third is the privacy. This is crucial because we track the equipment, not the nurse. So the system store no personal staff data. And lastly, the system relies entirely on the hospital existing Wi-Fi to transmit data, so avoiding the needs for new cabling. So this slide presents a high-level system architecture which follow a modular three-tier design. This structure was used to decouple the data collections for the processing logic, making the system easier to scale. So at the bottom, we have the hardware layer that consists of ESP32 microcontrollers. Their only job is to continuously broadcast their unique identity via the Bluetooth Low Energy BLE. They are dumb device, so they don't know where they are. They just shout, "I'm here." So in the middle is the client tier, which is the Android applications. This acts as a mobile gateway. So it listens to the BLE signal, capture the signal strength, and combine it with the phone current Wi-Fi BSSID, which is Basic Service Set Identifier, also known as MAC address. So it bundles all these contacts into a JSON payloads and transmits it securely over the hospital existing Wi-Fi network. And finally, at the top, we have the application and data tier. The PHP backend server receives the payloads and runs the location resolution algorithms and store the results in the MySQL database. And the web dashboard that queries this database to show the live location to the nurse. So this separation ensures that even we add thousands of beacons, the server handle the loads, not the phone. So for the hardware, I configured the ESP32 to strictly follow the standard iBeacon protocol using Apple's company ID 0x004C. So this ensures that the beacons are universally detectable by any standards of Android or iOS device without requiring custom firmware modifications. So the core of the threading logic lies on the packet structure. I utilize the three parts hierarchy. First is the UUID, which is a universally a unique identifier. So I assigned a single static project UUID to the every beacon in the system. So this acts as a security filter. The mobile end is programmed to only listen to this specific UUID and ignore all other Bluetooth noise, such as smartwatch or headphones. So second are the major and minor value. I use the major value to encode the category. For example, 100 represents ventilator, and I use minor value to encode the specific unit. For example, 5, which represents ventilator 5. So this allows the system to distinguish between the ventilator and the infusion pumps instantly. Then I also set the advertising interval to 100 milliseconds, where the standard beacons might broadcast every 1000 milliseconds to save battery. I increase the frequency to 10 times a second. So this is a critical because the hospital staff are often working too fast. So 100 milliseconds interval ensures that the phone capture enough signal data points to perform the smoothing algorithm effectively, even where the user is in motion. So this slide details the logic inside the Android applications. I specifically designed this to be a battery conscious because we cannot ask nurse to charge their phone 3 times a day. So to achieve this app uses sleep-wake cycles. So it doesn't scan continuously like a GPS navigation app. So instead it says in the deep sleep mode to preserve battery. So every 10 seconds the timer triggers a wake up events. You open a short active scanning window to listen for the signal and then immediately go back to sleep. So during the open window, we perform edge processing, so meaning that we process data on the phone itself rather than sending raw noise to the server. And then the first step of this is UUID filtering. So the hospital is full of Bluetooth noise from patients' headphones and smartwatches. So the app checks every signal against our specific project UUID. If the ID doesn't match, the app discard the packet instantly. So this ensures that we only upload the relevant high-quality data to the backends, reducing the server loads and bandwidth usage. So this slide covers our first critical algorithm, which is RSSI, Receive Signal Strength Indicator Smoothing. So one of the biggest challenges in the hospital environment is multi-path interference. Hospitals are full of metals, beds, trolleys, and cabinets. So Bluetooth signals bounce off this surface, creating a fading effect. It means that even if a nurse is standing still 1 meter away from a ventilator, the raw signal strength might jump from negative 60 dBm. dBm is a decibel milliwatts, a unit to measure the power of telecommunications at radio frequencies, and to negative 90 dBm into split seconds. If we display this raw data, the item would appear to be jumping around the room on the screen. So to solve this, I implemented a simple average SMA algorithm. Instead of trusting a single scan, the system collecting a buffer of last 5 RSSI samples and calculate the means by using the formula shown in the slides. So I specifically choose window size of 5 because my testing shows that it offers the perfect balance. So it's a large enough to filter out the noise, but small enough to remain responsive when the nurse is walking fast. So once the signal is moved, we move to the second algorithm, zoom classifications. So many commercial systems try to calculate the exact coordinates, telling you the atom is 1.5 meter away. So in a massive hospital environments, this position is often a lie and leads to user frustrations when the number fluctuates. So instead, I designed the system to use logic zones based on the specific signal threshold derived from my calibrations testing. So if the signal is stronger than negative 50 dBm, the system classifies it as an immediate, meaning that the item is within arm's reach, less than 1 meter away. Then if the signal is between negative 50 and negative 75 dBm, it is near, so roughly 1 to 3 meters away, likely in the same room. So anything weaker than the negative 75 dBm is classified as far. This approach is much more reliable for the medical staff. They don't need to know the exact centimeters. They just not need to know if the equipment is right in front of them or across the room. So the final algorithm is handle the location resolutions on the server. So first, we use the Wi-Fi fingerprinting. The system maps the router unique MAC address BSSID to a human-readable room name, like Ward A. So second, to handle conflicts where two nurses detect the same item simultaneously, we use the deterministic rule. The system trusts the scan with the highest RSSI, So I'm assuming that the phone is physically closest to the asset. So this data flow diagram is trace the complete data life cycles. It starts from the beacons broadcasting a signal, the mobile intercept this, and bundle it with the current Wi-Fi BSS ID and transmit the JSON packets via the API. So the database store these transactions, and finally the web dashboard pulls the latest status to display the live locations. So this is a linear real-time pipeline. And also, the system relies on a normalized MySQL database. So the three critical tables are beacons for hardware IDs, locations for mapping Wi-Fi routers to rooms, and tracking logs for history. So a key features here is privacy. It does log and store a hash device ID, device underscore ID underscore hash. So this allows us to deduplicate data from the different phones without ever recording the personal identity of the medical staff. And let's come to the API specifications, which happen via a secure JSON post request. So the payload structure is strict. It includes the beacon UUID for the identity, and the RSSI from the Zoom calculations, and the Wi-Fi BSS ID from the room locations. I also include a timestamp to ensure that the dashboard always shows the most recent data, even there is a network lag. So this is a mobile scanner interface. I designed it to be completely passive. So nurse just need to see the green check mark to know it's working. There are no complex menu to navigate. Simply runs in the backgrounds and counts active beacons, so ensuring it doesn't distract them from patient care. So this is the main dashboard for the medical staff. The live location features is the core feature. So a nurse can instantly see that the ventilator is in the radiology and was last seen 2 minutes ago. So the summary cuts at the top and also alerts them immediately if any items are missing from the network. And this is a equipment management module. Here, the administrator links the physical beacon's UUID to the actual digital asset name. So this translation layer is crucial so the dashboard display portable X-ray machine instead of raw, confusing technical ID codes. So for easy maintenance, I built a secure admin panel featuring calibration sliders as a password and an admin ID to log in. And since signal physics vary between different room size, so this will allow IT staff to adjust the near and far sensitivity threshold dynamically without needing to rewrite any codes. So to validate the system, I use a ground truth testing methodology. I will use the physical tape measures to verify that the zone classification is over 90% accurate. So I will test the system latency by walking between rooms and ensuring the dashboard updates the new location in another 5 seconds. So as a conclusions, this project successfully bridged the gap between the expensive commission system and the need of efficiency. By leveraging the mobile crowdsourcing, I created a solution that's low cost, requires zero fixed infrastructures, and effectively solves the equipment search problem for hospitals. Thank you.